I'd like to thank you all for getting up early and showing up for my talk. I'm not sure I would have gotten up early and showed up for my talk. But so this is a cut-down version of the Turing lecture that John Hennessy and I gave at the architecture conference last June. So I'm going to do 50 years of history in about 15 minutes, talk about some challenges, big challenges facing our field, and then what are the opportunities there. But first, there's some lessons from these last 50 years which we're going to apply repeatedly. The first is that we get inspired by software advances. Oh, look at those guys doing. I wonder if we could do that. Basically, if you can ever raise the level of the software-hardware interface, it creates opportunities for us. And then finally, we do things that people invest billions of dollars in, and so we get them to invest billions of dollars, and the marketplace settles that, as you'll see. So let's go back 60 years to IBM, and they had this big problem. They had 4 incompatible product lines. Each had their own instruction set, their I/O systems, software stacks, and different business niches too. So engineers at IBM decided they wanted to fix this. They wanted to have a single instruction set to unify all these businesses together. So that was a bold idea 60 years ago. But they needed a technique because the hard part of computers then as now, as we know, is the control. It's not the data path. So Maurice Wilkes, a Turing Award winner and a computing pioneer, had invented this idea that he was trying to get people to use. Let's specify control in a memory. So let's specify control. And he called it a microprogram. So you could, and it made sense at the time because logic was more expensive than memory and ROM was faster than RAM. So he said, let's specify control by filling in a ROM. And he called those micro instructions or microprogramming. Now, so what IBM did amazingly in 1964 is, and no one's really done that since, is announce many computers on the same day. They varied in datapath width by factors of 8, and in clock speed, and in memory speed, and so on. And in price, they all ran the same programs, but in today's dollars, it was from $1.5 million to almost $9 million. So IBM bet the company on this idea, and they won the bet, and IBM dominated mainframes then and even now. It's a $10 billion a year business, and one of the persons who led that was Fred Brooks, he led the 360 effort, and he was a Turing Award winner too. Let's go a few hundred miles north to Boston and talk about mini computers. Now everything's done in transistors, logic RAM and ROM, and RAM is about the same speed as ROM. Moore's law applies, so control store could get bigger, and since it was RAM, you could fix bugs a lot easier than if it was ROM, which enabled much more complicated instruction sets with a bigger memory and alterable. And the classic example is the DEC VAX 11780, which had a lot of microcode, very wide. Now let's go 3,000 miles across the country to the West Coast and microprocessors. And now microprocessors are 8-bit microprocessors, but they're rapidly gaining in because of Moore's law. And what they did, because they didn't understand computer architecture, but they didn't understand silicon, is basically imitated what the big guys did. So the way they innovated, because people were programming assembly languages in these little tiny computers, was they'd add a whiz-bang instruction and show an example in assembly language how to use it. Now, Gordon Moore was nothing if not visionary. He believed back in those days that the 8-bit microprocessor, that the next instruction set they did would last as long as Intel would. So he hired a bunch of PhDs, sent them to Oregon and in Portland, and created a very ambitious project. The PhDs did that. They called it the 432 eventually. It was certainly the most ambitious project of probably the 70s and 80s, and it started in 1975. They were going to do a 32-bit capability-based addressing. That's something we're talking about today in the RISC community. An object-oriented architecture. The instructions varied in bit length from 3 bits to 17 bits. A custom operating system written in Ada. So really ambitious. Alas, that ambition was punished by performance problems and ran late, so they had to come to their founder, Gordon Moore, and say, look, we're not going to be there in time with a 16-bit microprocessor. So that set off alarm bells at Intel, and they started an emergency project to try to build a 16-bit computer in just 52 weeks. Given 52 weeks, they only spent 3 weeks on the instruction set. 3 weeks on the instruction set. So 3 people, 3 weeks on the instruction set, and they basically extended the 8080 8-bit one to 16 bits, a little bit more than that. To their great fortune, IBM needed a 16-bit computer. They loved the 68000 as a relatively elegant instruction set, a lot like the 360 instruction set, but it was late. So they went with an 8-bit version of the 886. But that wasn't that big a deal. People weren't that excited because IBM thought they would sell 250,000 over 5 years. You know, not that many. But they were wrong. They sold 100 million instead. And so 886 suddenly became an overnight success because it is binary compatible with PC software, which was going to dominate the next few decades. Now, what brings us into the RISC community, that analyze these microcoded machines. The big thing that happened is that the whole field, or everybody moved up to high-level language programming. Unix demonstrated you could even write an operating system in a high-level language, so there was no excuse to writing assembly language. So now we cared what the output of the compiler was in evaluating our instruction sets. So John Cock, a Turing Award winner of IBM and a pioneer in architecture and in compilers, thought he would do this experiment based on the work he had done with his compilers, and that experiment was to take this mainframe instruction set and only use the relatively simple instructions, the loads and stores and the ALU instructions. What happened? It ran faster. If you avoided the complicated instructions, you could run faster. That's a surprise. And then the people at DEC in Boston studied the VAX architecture and found, first of all, that it was a lot slower than people thought it. The average clock cycles per instruction was 10. They thought it was more like 5. And most of the microcode wasn't used. A few instructions were most of the microcode and almost never executed. I took a sabbatical at DEC that time and to help on microcode bugs, because that was my dissertation, and was impressed how complicated that was, and it was going to be really hard to get bugs out. And I came back, and that led my entrance kind of to the RISC idea. So what's this? How did RISC evolve from the CISC? Instead of the RAM using it for microcode interpreters, we're going to turn it into an instruction cache. So that's a big step. It's kind of like compiling versus interpreting. And then, of course, since it's a cache, when you change the program, what's in that fast RAM changes. So that's an advantage. It's a really simple instruction set, as simple as microinstructions, just not as wide. And it was easier to pipeline these simple instructions, which helped. And the complicated instructions we were throwing out didn't help that much anyways. And then another breakthrough from IBM people is they had a really nice register allocation scheme which made the load store architectures even more effective. That's where Berkeley and Stanford entered the scene. So this is RISC-1, and I had the prescience to get a group picture at the time. So this was it was done in a series of courses in 1982 is when it was finished. There was RISC-2, which was a much more efficient design, was done by a couple of those graduate students the following year, and then that's also when John Hennessy led the MIPS group. And this was this remarkable moment in time when we went to ISSCC in 1984, where these two designs were presented, and I was in the audience, and you know, when they were presented, there was murmur about this. And it was remarkable because graduate students, a handful of graduate students at Berkeley or at Stanford, could arguably build on their own a microprocessor that was better than what an industry could build. At the time, we had a hard time explaining how these simple instructions could beat these complicated ones, because you didn't have to execute as many, and this formula basically explained it by breaking out time into instructions per program, CPI, and speed of the clock cycles. And basically, DEC engineers, to their credit, later published a paper that said, well, it's fewer instructions per program, say 3/4, but it's a lot higher CPI, so it ends up about a factor of 4 better. So at the time, these formulas were not in textbooks. So Hennessy and I decided to put formulas like this in the textbook, and I think it's possible that this is the first time that formula was published, was in this textbook. And it had a lot more formulas in it to try and make it more quantitative. And that happened in 1989. So wrapping up our history lesson here. So Intel, a great engineering organization, didn't take the challenge lying down. They figured out how to put 500 people on a single microprocessor design, and remarkably had a hardware translator to translate x86 instructions into simple RISC instructions. And then the RISC people typically at the time were the first ones to do something, and Intel would bring it along. And they had the tremendous binary compatibility to the PC instruction set. So they got up to 350 million microprocessors per year, and they eventually dominated not only the desktop, but the small servers. PC era, if the post-PC era starts with the iPhone in 2007, then the big change is we're not buying microprocessors from companies like Intel. We're building our own SoCs, and we're integrating IP from companies like ARM. So that's a big change. And so for these mobile things, it's not just performance plugging into a wall, but battery life and cost are very sensitive, which helps with a simpler design. They reach, last year, 20 billion. I'm sure it'll be more this year, chips that have RISC in them. And today, 99% are RISC. So this illustrates this. This is the marketplace settles these things. x86 wins the PC era. RISC wins the post-PC era. Okay, so that's the history lesson. What are the challenges facing our field, which are serious? No more, right? Moore's law is really over. This is Moore's revised slowdown law, doubling every 2 years. And Intel is off by a factor of 15 of where it should be if Moore's law still continued. So it's really over. People have claimed it before, but it's hard to find somebody who's going to claim it's not true these days. As important as Dennard scaling, we could keep putting more transistors on every chip because the transistors got more efficient by lowering the threshold voltage. Now it leaks, and so since about 2008 or so, the power, the density, the power per unit area is up and to the left. So power is now the big challenge. This turns into performance. The ending of Moore's law, the ending of Dennard scaling. Back in the good old days, I tell young people back in the 80s and 90s, people would throw away working computers because their friend's computer was 2 or 3 times faster because it was newer. Nobody throws their laptop away today until it's broken because single program performance has barely improved at all. Last year, it went up 3% according to Spec Int. And when you stop getting better, people can catch up. I think it's a significant event that a RISC processor by Apple, the A12, apparently is as fast as the Intel laptop's processor. It is now or will soon be. So this is, RISC coming back on top in the performance for single thread is a significant event. All right, so no more Moore's law, performance isn't getting any better. What else? Security. So the Spectre attack that speculation can leak information. Before, timing didn't matter, according to IBM. It was as long as it's compatible, you didn't care about the timing. Timing can leak information. This is a serious attack on our principles of computer architecture, and it's not going to be easy to fix. So we're going to have to take that on. So that sounds pretty bad. No more Moore's law, performance is over, and the way we build microarchitectures is vulnerable to leaking information. We're making things work. It's not the software work, it's the architecture's worse. So, what are the good things we have going? Why was it open source software but not open source open ISAs? And so doing a quick version of what a lot of you guys know, I think it's the free and open part. Anyone can use it. It's got to lead to more competition with lots of more companies building it and more innovation. I don't know how many open cores there are already. Is there 8 already? And lots of licensed cores, and I'll talk about that. And as Krista said yesterday, it enables this new business model. I'm going to go with RISC-V. I'm not going to sign a contract before I get started because there's lots of people who could supply it. It works for both the cloud and the edge. I think most of us think the cloud and the edge are the future of the industry, and it's going to work both places. A lot of countries are worried about what's inside the microprocessors they're deploying in their infrastructure. If you get to design it yourself, you know what's in there. So countries all over the world are concerned about that. And the open cores may make that help as well. And then it really is simple and elegant. It's really, because it's driven by technological issues, not marketing issues, there's no marketing reason to expand the instruction set. And it's a new idea in an instruction set in that in the past you had to be binary compatible, upwards binary compatible, and if you stuck it in, you had to leave it forever because you don't know who's going to run things. RISC-V doesn't do that. RISC-V says you can add custom instructions. It won't break the software stack because the software is only based on the core, not on the extensions. And I'll explain why we need the custom instructions. And then what's another thing that's different about this instruction set because it's open is, instruction sets, if they're successful, will last for 50 years or more. I think RISC-V will last as long as everyone is in this room is alive. So we got to get it right because it lasts forever. Classically, instruction set architecture, the company announces it, then they get the feedback from the software people, then they amend it, and they keep doing iterations. So we're trying to do it differently, but it's going to take more time. We're trying to reach agreement with experts, hardware and software governments, and then we do the standard, right? We're doing it more like a standards effort. So it's slower, which is frustrating because it's slower, but it's more careful, it's going to get it right, and if it's going to last for decades, our descendants are going to be really happy we took our time to do this. And then the big deal, of course, is it's, a company doesn't own it, a community owns it, and no matter what happens to a company, RISC-V is not going to go away because there's a foundation. The foundation is up and to the right, hundreds of them, and then I'm going to take my time and explain everybody's going to get the open architecture versus open implementations, open source implementation. So there's two things. There's specifications like an instruction set, like RISC-V. Another example of that is POSIX. This is actually an IEEE standard for operating system interfaces. So those are specifications. Then there are designs that are typically on source code. And so RISC-V Rocket is an example of the design. And so is Linux. Linux is an example of design. So this is an implementation of that specifications. And then there's products that are based on those designs. So specifications and designs, there's 3 flavors of these. It's free and open, and I'm using traffic light colors. Green, free and open. Anybody can use it. There's no fee. You can design it yourself, and you can share it with others. So if you can share it with others, you can get it for free from others. That's all okay. There's licensable. That means one company owns it, and you pay a fee to use it. And you can't share it with anybody else or get it from anybody else but the company that owns it. And there's finally closed, red, which is there's one company that owns it and nobody else can use it. Okay, so specifications and designs, free, licensable, closed, so that's a matrix here, right? So we'll do the specifications on the left, the designs on the top, on the right. We have 3x3 metrics and there's products there. So let's start from the lower right-hand corner. Closed spec, closed design. Okay. That's like a Skylake for computer architecture there, or maybe the Windows operating system. Licensable, okay? So with a licensable spec, you can have licensable designs or closed specs. So licensable designs, there's ones from Sci-Fi, and there's NVIDIA is doing their own closed one. Now, if you did ARM, how much does that cost? It's a lot of money. It's $5 million plus 4% royalty for the licensable IP. And if you want to design it yourself, it's about $25 million. Okay, what about if it's free and open spec like RISC-V? You can do all of them, right? You can do all of them. But you need to have a free and open designs. You need a free and open spec. And that's what open source is that quadrant. So what can you do with that? Here's an example from one of Curtis and my former student, Zhangji Tan. He just announced this thing. It was in 28 nanometer. He did it from scratch. He did it himself rather than using Rocket. But he could do it in just 7 months, which is pretty remarkable. It's multi-core architecture, 64-bit, very energy efficient. It's got 12 AI engines in it. And remarkably, this board sells for $3, which it's hard to imagine how to do that. So we're going to see a lot of things like this now and in the next year, enabling this rapid innovation. What about security and open architectures? The security community doesn't believe in security obscurity. That goes back for centuries about trying to keep secrets. They like things open so you understand the algorithms. It's a simple architecture which allows formal designs. You can look at the implementations, see if there's no trapdoors, and you can change it. it and the instruction set architecture. But to me, it's embarrassing to me how bad security is. So, and especially since architects are now contributing to the problem, we need everybody who wants to work on this. It's not just people with badges at 2 companies. We need everybody to work on it. And by being open, we get all the best minds to work on it. And we need all the best minds to work on this. You think about what we did for the memory consistency thing. People have been arguing about that for 30 years. We probably made a pretty good design there. We need at least that level of effort on security. And what I'm excited about is my security colleagues can get into the synthesis game rather than the criticism game. Rather than complaining about Microsoft software, look, you have a weakness. We found a weakness. Why don't you try putting something up and see if you can survive, right? And RISC-V allows us to change the instruction set architecture, change the implementation, use an FPGA, get a full software stack, put it on the internet, and you could offer an award to see if somebody can break in. And the beauty of it is, because it's an FPGA, we could iterate like once a week or once a month rather than every few years, which is the current rate, and it's hard to be optimistic of changing it every few years. So I'm pretty sure RISC-V is going to be the exemplar for the security community. It's simple, you can modify it, you can put stuff out there, and I think the innovation is going to happen here first. So another opportunity is domain-specific architectures. Basically, all the architects I know think this is the only trick left. Single thread's not going any faster. We've already used up all multi-cores. Amdahl's law petered that out. It does one thing well that we can do. They use the word ASIC for the tool flow. It's not an algorithm in a chip. It's a domain that you need software to use. So it's more generally applicable. And why? So Hennessy and I, we do this quantitative approach. Is there some magic here? No, it's pretty understandable. We use things that didn't work as well for general purpose computing that are more restricted but more efficient, like SIMD over MIMD, VLIW over speculative. Those don't do everything well, but when they work very efficiently. Memory bandwidth caches are a great invention of the computer architecture community, and where you guess what you want to be there, but when they guess wrong, they can be a boat anchor. In a domain, you can know what you need to do with memory, and it's better under software control. The accuracy, grew up. Berkeley's proud of IEEE floating point, our Turing Award winner for that. But you don't need that for some of these applications. You don't even need floating point for some of these applications. Small integers can work. And then the big deal is, independent of us, domain-specific languages have been invented to improve the productivity of programmers like TensorFlow or PyTorch or Halide. But it raises the level of abstraction, which lets us innovate. So the example that I've been involved with at Google is the TPU, the first version of the TPU that was recently on the cover of Communications ACM. It's been in use for 3 years. If you go to Google, you're using TPUs when you do searches and things like that, and it helped the AlphaGo victory. The big deal there is two-dimensional multiplies are popular in machine learning, which is a great thing for computer architects. So it has 65,000 multiply accumulate units, and they can do one every clock cycle. So it's only 700 megahertz, but you multiply that times 65,000, so you get 90 tera operations per second, and that's a pretty formidable machine learning chip. How good is it compared to the chips of 2015 when you deployed? In performance per watt, it's about 80 times better than CPUs and about 30 times better than GPUs of that era. And performance per watt matters in this end of Dennard scaling. We had to use production applications when we did this evaluation because there are no benchmarks. The good news is now there's benchmarks. They were just submitted last month, and I think a week from today they go public, and that'll be eye-opening for everybody. So where are we in this architecture debate? You get, it's a really exciting time. It's kind of like one of these eras, Pleistocene eras, where all these species show up. I think it reminds me of the early days of multiprocessors when everybody had ideas what to do. So Google's betting on kind of a small number of cores per chip, a really big multiplier, and software-controlled memory. NVIDIA has lots of cores per chip, 80 right now, lots of threads, lots of registers, latency tolerance techniques. Microsoft is betting on FPGAs, so you can kind of tailor kind of the FPGA to the application. Intel's betting on everything. Intel bought the company that made the FPGAs that Microsoft is using. It bought companies that doing TPU like domain-specific architectures, and it's trying to make its general-purpose processors good for it. But besides all that, a few years ago we said there were no startups in hardware. There's at least 45 now that are around doing DSAs for machine learning. And so it's a very exciting time. The bad news, Moore's law is over, a crutch we've had for more than 50 years. Dennard scaling is over, that we had for 30 years. General purpose performance isn't going to be faster. If you're a software person, you're rating for the threads to go faster, you're going to have to rate decades. And we've got these terrible security challenges, so that's the bad news. But we've got some exciting new tools in our belt, open instruction set architectures, and I didn't talk about agile hardware development, but that's going to be another advantage. And then domain-specific architectures versus general purpose, and that's why Hennessy and I think this is going to be a golden age for computer architecture. All right, thank you. So the timer hasn't gone off, and so I get 4 more minutes. But I need a question. I need a first question. Okay.
Is there anything we can be doing to help people migrate from their x86 code to a new ISA?
So about the cloud. Right now, I retired, but I'm spending a day a week at Berkeley. We're working on a Berkeley view of serverless computing. And if you haven't heard of serverless computing, it's kind of an oxymoron, but you take functions written in programming languages and upload them to the cloud and run them. So it's raising the level of abstraction. So we believe serverless computing compared to the traditional virtual machine. Serverless means you don't have to be a system administrator and manage a virtual machine. So there's serverless out there. It's called Lambda functions in AWS and cloud functions at IBM and Google and Microsoft. So this is raising the level of abstraction. And so that's going to allow us to innovate below that, not only change the instruction set architecture, but to do things like I was talking about, like domain-specific architectures for things like TensorFlow. Last week at Amazon's big event, they announced their own inference engine, Inferencia, and it's not available in the virtual machine. They're providing a machine learning service, and it's going to power that. So I think that's what the future is going to look like.
Thank you.
Mm-hmm. Yeah, I'm excited about the serverless. I thought it was x86 binaries forever in the cloud, and it looks like that's changing. Other question? Usually the first question, oh, there they are, here.
Thank you so much for the history lesson, actually. That was fantastic.
I'm a teacher, so.
Yes. Can you talk more about how architects contribute to the problems of security?
Yes. It's another history lesson. When IBM invented computer architecture, we didn't use the term before that with IBM 360. They said, what is architecture? It's everything you have to know to get the program correct. So you have to know, what do you have to know? Registers, the instruction coding. So to get a machine language program correct, that's the definition. Timing didn't matter because they wanted to have a family of computers, right? They wanted slow ones and fast ones. It turns out, because of side channel attacks, if you are sharing a resource, people running elsewhere can watch how long it takes and trick you into using something that's data dependent, and it can guess at a low rate. It can guess what the value is, and in particular, it's speculation does this, because the way we build microprocessors today, or the highest end microprocessors, we guess what's going to happen. And we can't really afford to roll everything back, cache misses and all that stuff. We guess what's going to happen. When we're wrong, we just move forward. But that guessing leaks information, and that's kind of shocking. I would have thought, oh yeah, what are you going to, 1 bit a month? Oh no, it's K bits per second, and they can discover secrets right now. And so it's shaking the roots of computer architecture, and so it's going to be a not trivial thing to figure out what to do. It's not like, oh yeah, I have a patch for that.